All right, guys, let's continue our discussion about ligand binding. And you remember from the last section, we ended with a discussion of sort of the next more complex case of simple binding of a macromolecule with two binding sites, excuse me, but where the affinities for those two sites are not equivalent, right? We went through the macroscopic derivation and the microscopic derivation. You end up with two mathematical equations that are essentially equivalent to each other, but we talked about how those macroscopic and microscopic binding constants mean something different. They're related to each other, but those numbers aren't going to be the same, and they're not going to be the same for those fundamental statistical reasons and sort of the assumptions that go into setting up that derivation. Now, the way in which you would sort of get at those numbers, assuming you had data that suggested, or experimental system that suggested you had a protein with two sites, they didn't have the same affinities. You'd, of course, plot the data using a standard binding plot or a titration binding plot. And then using a data analysis package like UGOR-Pro, you'd encode the appropriate fitting function, either the macroscopic equation or the microscopic equation. And you'd fit. You'd run a nonlinear regression and see if you could extract those parameters. And that's more or less the same basic approach, even if the binding model got even more complex, right? More binding sites, right? You could derive similar equations, use a similar approach for multiple independent binding sites. Now, where things get a little bit complicated is on a couple of fronts. One, when those binding constants, either the microscopic binding constants or even the macroscopic binding constants, when those start to get very close in magnitude, it can be difficult within the error or noise of a real experimental measurement to get an accurate fit. Sometimes the way nonlinear regression works, the way those parameters get coupled together in the process of trying to do the minimization can make it hard to get a robust fit. So that's one issue. There's another issue that has to do with what kinds of plots people use. This is somewhat less of a problem nowadays with modern computers, but once upon a time, this was a major issue when we were back in the line, and the slope and intercept and graph paper era, and it had to do with applications of the scatter plot to situations like this. So if you remember, scatter plot, of course, is this linear transform of the basic simple binding equation. And imagine a situation where we had, I'm not going to derive it for multiple sites. We're just going to, think about the graphical characteristics here. And you remember that the degree of binding divided by, for example, concentration of our ligand relative to the degree of binding. And if you remember, for the way this was supposed to work, if you had nice, simple single site binding, you get a nice line of negative slope. Where that slope is, of course, equal to, the slope is, of course, equal to minus of the association constant, or minus 1 over the dissociation constant, right? The binding stoichiometry, or N, is the intercept down here on the x-axis, right? And technically this intercept up here is N times the association constant, or N over the KD. All right, that's fine. The problem comes in what if you had one ligand, right? But a protein that could bind two different binding sites, and if they had two different affinities? Well, in a situation where, like I said, you now have two binding constants. Say we have a K1 and a K2. So we have two sites. So we're fundamentally looking at a molecule that looks like this. If K1 binding to one site is much greater, right? Or I guess if I'm going to use, let's use the microscopic in this case. Let me switch back to using kappa. If kappa 1, let's say, is much greater than, or much smaller than, or much greater than the intrinsic affinity for the other site, you get a characteristic scatter plot. It does something like this. Plot would go, right? And you sort of get this two distinct zones, which would be a, relative to the binding constant for the two sides. You almost get like two linear plots sort of combined together. The problem is that's unusual, right? Unless these things are really just dramatically different from each other. In affinity, that's not usually what you would see in a situation with a macromolecule with two binding sites, independent binding sites, different affinities. What more likely to happen is you get a plot that looks like this. Still deviates, it's not linear, but it's curved, so-called concave up plot, right? Sort of a scatter plot. And the problem with the scatter plot, this is one of the problems with the scatter plot, one of the reasons it sort of fell out of favor, is because that is a easy way to get a scatter plot is exactly the situation I've described, where you have a macromolecule, two independent binding sites, different affinities. You're gonna end up seeing a concave up scatter plot. But there's another way to get a scatter plot that looks like that, right? And that's when these two binding events, say, are not independent, right? This will also give a concave up scatter plot, and specifically, it's a type of interaction or coupling between the plots when they're not independent. That's known as negative cooperativity. Right? And the problem that people got into using the scatter plot is they would have a molecular system, they do an experiment like this, they convert it to the scatter plot, they see this concave up plot, and they go, aha, I clearly have negative cooperativity in this system. And there were lots of examples of that where it turned out, no, that's not what's going on. All you really had was you had some wild type protein and you had some damaged protein, right? The specific activity wasn't what you thought. You got partial binding to one, and it's basically dirty protein or dirty enzyme. There are lots of examples of incorrect characterizations of cooperative systems using the scatter plot. It's one of the reasons it sort of fell out of favor, in addition to the power of sort of nonlinear regression and the sophistication that computers bring to doing this kind of analysis. But this is sort of a nice way for us to segue into this issue, of sort of cooperativity, which is another way of talking about the next subject we want to dwell on, which is this idea of linkage, or more correctly, thermodynamic. Linkage between two binding events, right? So say, again, I have a macromolecule that can bind with intrinsic affinity A and intrinsic affinity B, some ligand A, right? Bind to either of these two sites. But what if occupancy in one site now influences, right? If the B site was occupied, this now influences that affinity in some way, right? They're not independent events anymore, right? So this is the sort of fundamental idea behind thermodynamic linkage in ligand binding, and it's a biggie, right? In a big picture sense, this is very similar to the idea of linkage that we talked about in protein folding. The idea that these interactions, each interaction as you build a folded protein, is not independent of all other interactions. Same kind of idea, but it's expressed or it shows up in a somewhat different way when you start thinking about ligand binding. It's the same idea, but we got to sort of think about it in another way with respect to how different sites get saturated in the macromolecule. All right, so let's take this idea and abstract it a little bit, sort of illustrate this for you guys in a different way. Let's again take our macromolecule P, right? And we're going to bind potentially two different ligands. This time, I'm going to talk about two different ligands rather than the same ligand where the binding sites sort of influence each other. We're going to talk about two different ligands, this is the much more well, I don't know if it's more common, but it's the more general case that we want to think about. So let's say our macromolecule P can bind a ligand A, right? And we'll give this sort of intrinsic affinity K sub A. So now we make the PA complex. But this molecule can also bind a macromolecule B, right? With intrinsic affinity K sub B. Again, remember these are dissociation constants, it's the way biochemists are usually going to think about it, to make complex PB. Okay. But our molecule has two sites, one a site for binding ligand A, specific to ligand A, and a site that's specific for ligand B. So we don't have to stop there, right? We can say, okay, well, this guy can then go on, right, and bind ligand, after binding ligand A, can bind ligand B. To form the ternary complex, A, B. And we can go this way too. After binding B first, we can now bind A, right, to bind the ternary complex. Now we have dissociation constants associated with that situation as well. I'm gonna write them a little bit differently. This one I'm gonna give sort of the K A slash B. And what that means is the binding affinity for B, assuming A is already on the macromolecule, that it's already bound A. And we have a symmetric constant down here, which we'll call KB slash A. All right, so here's the question in this model, right? What happens if we start out here at P, right? And we go all the way around, we make this complex here, and then we come all the way back around again. Thermodynamically, what would that mean in terms of the free energy change? Delta G, right? If we started at P and came back all the way around to P. So let's say we started at P, went through the BPA complex, and then came back around to P again. It's zero, right? We sort of started in this state, free energy. This is exactly the kind of thing we talked about when we talk about state functions. The free energy change of P on its own has some value of G, right? And if we do come all the way back around again, the delta G, the G minus G to be the same, is going to be equal zero, right? So the full cycle is going to be equal to zero if we assume we're at equilibrium, right? That full cycle has to equal zero. All right, so we got that down. That's not such a big deal. All right, so what about this case? What happens now if we start here at P and we go just this half reaction? Or say we could start here at P and we just go this way. So we got sort of the two half paths. Well, because we know delta G for the full cycle at equilibrium has to equal zero. That means delta G, say, let's call this delta G top minus delta G bottom has to equal zero, which means delta G top has to equal delta G bottom, right? Or another way to put this is that the free energy change for the two half paths around this so-called thermodynamic cycle have to be equal to each other. So if the free energy of the top path has to equal the free energy of the bottom path because of our assumption of being at thermodynamic equilibrium, what that means, if you were to go through the derivation, what you would find out is that if you think about the equilibrium constant for this overall process for the top half and the bottom half of the cycle. If you set up the equilibrium expressions and you go through the algebra, what you find, of course, is that the equilibrium, the overall equilibrium constant for the top path, so we'll just call this K top, is just equal to Ka times Ka over B. The equilibrium constant for the bottom half of the cycle is just equal to Kb times Kb over A. Okay, but because of the free energy condition we just set up, the other thing we know must be true is that Ka times Kab has to equal Kb times Kba, right? Because the free energies of the two half cycles have to be equal to each other. That's true, then the following has to be true. That I can rearrange that expression and the following ratios have to hold, which is that if I took the equilibrium constant for the binding of A, assuming B is already on the molecule, on the protein, and divided it by the binding constant for A to the unliganded molecule, that has to equal, it must equal the equilibrium constant of B, assuming A is already on the molecule, divided by the equilibrium constant of B binding to the protein alone. So what that very important relationship means is that the extent to which B being present on the protein impacts the binding strength, the binding constant of A, relative to how well A binds by itself, has to exactly match the extent to which A influences the binding of B. The magnitude of those effects and the direction of those effects. So if A makes B binding harder, B must make A binding harder. They're inextricably linked to each other. This is the fundamental idea behind thermodynamic linkage. And those symmetric effects of one ligand on the other are guaranteed by this simple thermodynamic cycle that we set up for how these two molecules are going to bind to the same protein. All right, that's the core idea behind thermodynamic linkage. And this idea of linkage is going to get us to an understanding of ligand cooperativity, binding cooperativity, which we're going to begin discussing next in the context of oxygen binding by hemoglobin.